no? It makes sense, but I cannot prove it. What does that mean? No? Okay, finally. So I will write one more step. So epsilon transpose. If you write out as a matrix, this is a column vector, this is a row vector. It will give you n by n matrix, okay? So on the diagonal, you have sigma 1 squared, sigma I squared, sigma n squared. Off diagonal, it is sigma ij. This will be sigma ji. I would say sigma I, sigma j. Okay, sigma j, sigma I. And if you apply E, expectation, you basically apply expectation for each element. Okay, so each element, this will be E of sigma 1 squared. This will be E of sigma n squared. This will be E of sigma I, sigma j for different ij, and similar, because this is, although you cannot say it's symmetric because each one is IID here. So E, you can say sigma j, sigma I, different rows and columns here. So once you have that, you realize if two are independent, E of epsilon I, epsilon j equal to E of epsilon I times, I will write one more step here. So on the diagonal, it will be E of epsilon 1 squared all the way to E of epsilon n squared. But this will be just E of epsilon I times E of epsilon j. We can do that because they are independent. But two independent variables, E of AB equal to EA times EB. And similar thing here. So this will be E of epsilon j, E of epsilon I. Okay? Then you plug in the E of each epsilon is 0. So you basically have on the diagonal, you have E of something squared, E of epsilon I squared. Okay, on the diagonal. Off diagonal, you have 0. So what is E of epsilon I squared? So E of epsilon I squared is just the variance of epsilon I plus E of epsilon I squared. By the definition variance, it equals the difference between E of the square form minus the square of the E. So what is variance of epsilon I? Sigma squared, right? And E of epsilon I is 0. So it's equal to sigma squared. So eventually you have on the diagonal, you just have sigma squared. Off diagonal, it's 0. So that's why it's equal to sigma squared times I. All right? Okay. So that is the remaining part for section 3.6. So next we enter section 3.7. So once we have the estimate for sigma square, we can talk about the sampling distribution for the beta square, right? We have beta 0 hat, beta 1 hat, all the way to beta p hat. So what are the sampling distribution of beta j? Okay, j equal to 0, 1, p. You have beta 0 hat, beta 1 hat, all the way beta p hat. So in the simple linear regression, we talk about beta 0 hat and beta 1 hat separate. But here, because we adopted the matrix form, we no longer need to separate them. We just basically use the matrix form to derive a vector of j hat. Then you can take out what you need, the information you needed from the vector, and also for the variance, it's matrix. You take out what you needed from the matrix. So what is beta hat in matrix form? It's X transpose X inverse X transpose Y. Okay? So sampling distribution here, remember 3 pieces, what kind of distribution it is, and also the parameter of the distribution. So from here, you know that each of the beta, no matter what is value for j, from 0 to p, it's a linear combination of y, right? Because x here is not considered a random variable, it's considered a constant. So each row of beta, this is a column vector, each row of this vector, each element of beta here is a linear combination of all the y's. Y follows normal distribution, so what kind of distribution should be each of the beta j hat? It is normal, right? So once we learned it's normal, next we look at what is expectation. What is E of beta hat? This should be pretty easy because x is considered constant, so you basically have E of X transpose X inverse X transpose Y. Okay? And then you take out before we take out the constants, we basically have X transpose X inverse X transpose spread Y as X beta plus epsilon. Okay. Then you basically have E of X transpose X negative X transpose X beta plus E of X transpose X inverse X transpose epsilon. Okay. Now, inside here, what is the randomness? Where does the randomness come from? This is X. This is beta. It's a true parameter. Then this one, inverse multiplied by X transpose X. It gives you the I, right? It is a identity matrix with p plus 1 by p plus 1 dimension here. And you just have an E of beta. Beta is true parameter. Okay, so the first part give you just beta. It's a vector. But the second part here, X is considered constant. You basically have a constant multiplied by E of epsilon. E of epsilon, each element of the vector is 0. So together it's still 0 vector. It's a 0 vector, so it still give you beta. All right. So this is the expectation. What about the variance of beta hat? So variance, a constant term multiplied by a random variable. Basically, you square the constant part. But however, this is not scalar. You need to make sure you have the quadratic form, but you need to also make sure the dimension that is compatible in order to do matrix or vector multiplication. Why the second term is 0? Because E of epsilon gave you a 0 vector. Okay, the first part is considered constant. All right. So in order to write out in a form that the dimension is compatible, you basically write out the first part just as it is. Okay, then you have variance of y. The second part, in order to do multiplication, you need to transpose it. Okay, transpose the whole constant part. Basically, you get X transpose X inverse. Okay, so what is variance of y? Y is vector, variance y is a matrix. Variance y equal to sigma squared multiplied by I. The off diagonal is 0 for the same reason, because each y is independent. Okay, then you take out because this is multiplied by I, you take out sigma square, you get X transpose X inverse X transpose X. Then you get X transpose X inverse again. And these two can cancel. So basically you can cancel one pair. You still have X transpose X inverse here. So this is when the true sigma square is known, you get variance of beta. If the true sigma square is unknown, you basically need to use the estimated sigma hat to replace it, okay? So remember, beta hat is vector, variance of vector you get a matrix from. This is still a p+1 by p+1 matrix. So how do you get the variance and the covariance? So variance of each beta j hat. This comes from the diagonal position. Let's say I'm taking X transpose X inverse equal to a matrix called C. I'm basically redefine X transpose X inverse as a new matrix C. So I want to take the variance of the J's element here. It will be on the J's diagonal position, okay? The variance all come from diagonal position. So variance of beta j hat here equal to sigma square times Cjj, okay? Where, what is Cjj? It's just the j's diagonal position. Is the j's diagonal element of C. C is X transpose X inverse, okay? The j's diagonal position of X transpose X inverse. So we get the variance. How about covariance? Do you have any reason to believe the off diagonal will be 0? We don't, right? Unlike when we talk about the variance or covariance matrix X epsilon epsilon transpose. Here we are talking about X transpose X inverse. So because the C here off diagonal position is not guaranteed to be 0, okay? C equal to X transpose X inverse. So off diagonal may be non-zero. So in that case, there is covariance between beta I hat, beta J hat, okay? So that basically comes from the ith row j's column of this C. So equal to sigma square multiplied by Cij, where Cij is the ij cell of X transpose X inverse. Okay, ith row j's column. All right, now we have E, we have variance. We can conclude each of beta j hat follows normal distribution with what is the mean? This is a vector form, right? Each of beta j hat here equal to beta j. What is variance? Variance of beta j is sigma squared Cjj, okay? Any question for this part? So this is when you assume the true variance sigma square is unknown. If it is not, you use a sigma hat square to just replace it. It will be estimated. Okay, so this is your takeaway from all the derivation here. So if we ask you to derive what is sampling distribution of beta j hat in the multiple linear regression, this is all it takes. Of course, you have to say something why it is normal. Okay, it's a linear combination of why it's normal. You have to state it. All right. So we also want to add a few words about the properties of the estimated sigma hat square, defined as SSE over n minus p minus 1. First, we know that it's unbiased. This is already proven. And 2, we also know, although we don't prove the chi-square distribution, but we do use it sometimes, because later on when we try to do testing, there will be t-test. T-test come from the, first you have a definition for the chi-square. So the n minus p minus 1 sigma hat squared divided by the true sigma squared. This equal to just SIE divided by sigma squared. This one follows chi-squared distribution with n minus p minus 1 degree freedom. And the third is also important. The beta j hat we just learned the distribution for, and the sigma hat squared. These two things are independent. Okay, all these are the foundation we can derive in order to do a t-test. Okay, without the independency, remember I give you the definition for t-test earlier. It requires the z on top and also the chi-squared at the bottom. These two are independent. Without the independent assumption here, we cannot conclude the test statistic we found are t distributed. Okay, so we are going to do t-test for beta j later. So this is the foundation here. All right. Question? All right. So next we move on to the section 8. Section 8, we want to say a few words about the coefficient of determination, R squared. R, as we defined before, is called coefficient of determination. So in SLR, simple linear regression, we define R squared equal to the ratio of SSR over SST. Do you think we can still use the same definition here? Do you think we can still use SSR over SST for multiple linear regression? Yes or no? Yes, okay. So basically, SLR generalized become as MLR. So the conclusion we have for SLR still holds for MLR. The one that comes from different line is RTO, regression through origin. So many conclusions that hold for SLR no longer holds for RTO, but it holds for MLR because we both have a intercept beta 0 in the model. So again, we also proved the relationship between the sum squares. We proved this is true. SST equal to SSE plus SSR. Each one is sum of squares is non-negative, so it's guaranteed SSR is less than equal to SST. Okay, so we can so totally guarantee this R squared is the value between 0 and 1. It's also equal to 1 minus SSE over SST. Okay, so R squared is guaranteed to be between 0 and 1. And also, in the SLR case, we did not prove, but it's true, that R squared actually equal to the correlation between y and y hat squared. Okay, and still true in MLR that R squared still equal to the correlation between y and y hat squared. Okay, this conclusion we did not prove. I think that the book have. I will ask actually in your homework. Okay, instead of giving you the answer here, I will ask you to do that in the homework. All right. So after we define R squared, we can define lowercase r. I believe we used the lowercase r before, but we can use, let's say R equal to R squared square root. Okay. Multiply by what? So in this case, in the simple linear regression case, it's easy to see this R is the linear correlationship between Y and X. It's also the linear correlationship between Y and Y hat, but the correlation between Y and Y hat is never negative. It's always positive. Okay, so here if we define R equal to the square root of R squared we defined here, the form give you is also non-negative. Okay, this no longer have a plus minus. So how do you interpret the meaning of R? What is the relationship we're talking about? I still accept that it's kind of a linear relationship, but in the simple linear regression model, it's a linear relation between Y and one X. Here you have multiple X. How do you interpret that? It should be the call that, first of all, the name is called multiple correlation coefficient. Okay, it measures relationship between Y and a set of predictor variables from x1 to xp. In the simple linear regression case, you only have one variable, so you can easily say, oh, it's a linear correlation coefficient between Y and X. But right now, it's a relation between Y, not with one particular predictor, but with a set. Okay, it measures the relationship between Y and a set of predictor variables all the way from 1 to p. Okay, so even though you get R, but that is pretty close to 1. Explanation, but the interpretation is always between Y and the whole set of xp. You cannot use that to explain the linear relationship between Y and one particular x. Okay, so that's the interpretation with the simple linear regression will be slightly different. All right. So what else is different from simple linear regression? And also, you know, in simple linear regression, if you compare two regression results, R squared, if one result have a larger R squared and the other R squared increase over usually is interpreted as basically the variation in Y can be explained by more of like amount of variation in X. However, with multilinear regression model, you have so many X here. If you use a different model, you add more predictor variables, R squared always increase. Okay. So also for the multiple linear regression, as you increase number of predictor variables, you increase to add more, R squared always increase. So R squared will always increase as you add more predictors. When we say increase, that basically means the new value will be greater than or equal to the old value, okay? It includes equal sign. So basically, it will not increase. It will either stay the same or add more value here. But usually, if you look at the definition for increase, it actually includes the equal sign here. So monotonically increase, but not strictly increase. If we say strictly increase, that will exclude the equal sign. When we just say equals, it actually includes the equal. All right. So in that case, how do we use squared as the measure of your goodness of fit? Because different people come with different model, you can always include more predictors to lift the value of R squared. So how do we know? Yes? I don't know this. Where's your question? You answered yes. Is quality bad for everyone else? What quality? A visual quality? The quality dropped a bit. Visual or audio? Audio. Oh, okay. You know, I'm using the IT Secure. This is IT network. I just don't know. It is already a lot better than the home network. So if you missed something, you probably just tell me which part you missed. Which part you missed? Last thing here. Okay. So basically, in the multilinear regression, if you add more predictor variables, the R squares will be greater than equal to the previous R squared. The larger model always have larger R squared, basically. And also, I emphasize here, when we say increase, it includes the equal sign. That basically means monotonically increase, but not necessarily strictly increase. Okay. So in this case, we still want to look at R squared as some measure of the goodness of fit. Basically, how good is your model to fit this set of data? So in this case, we need to adjust R squared to be the following. We call that R squared with ADG here. First few letters for adjust, okay? The new definition will be 1 minus, instead of SSE over SST, we will make each of them divided by its own degree of freedom. So SSE divided by n minus p minus 1, SST divided by n minus 1, okay? As you can see here, the degree of freedom SST does not change as you change your model. If you add more predictors, it is still n minus 1. But the degree of freedom for SSE here, if you add more predictors, p will increase. P will increase and n minus p minus 1 will decrease, right? It will decrease and SSE divided by a smaller value will become larger, and y minus that will become smaller. So basically, this one will avoid the problem we had before, which is R squared increase as you add more predictors. With this, we basically normalize that by its own degree freedom. Then you can use this as a measure for the goodness of fit, okay? So if we plug in the old definition of R squared, which is just 1 minus SSE over SST, is actually equal to 1 minus, then you get n minus 1 divided by n minus p minus 1, right? This is the constant part. Then SSE over SST will be 1 minus R squared, right? So this is the relation between the old R squared and the newly defined adjusted R squared. With this, you can compare different models. You can compare the two models. For example, y explained by x1, x2, x3. The other one, y explained by only x1, x2. Then you can compare the models based on R squared. Okay, use R squared ADJ. All right. So we haven't touched the topic of model selection yet. So in application, a lot of times you are the one to define your regression model. You are just given data, you have a lot of candidate predictor variables. You are the one to decide whether I should use this model or this model. Okay, so which one can be used for model selection? between r squared and r squared adjust. Which one can be used for model selection? Between r squared and r squared adjusted. Which one? R squared adjusted, okay? So answer is R squared adjusted. Then which one can be used to explain proportion of total variation in Y that can be accounted for or explained by the total variation in X? Not X, I would say X. With the plural between R squared and R squared adjusted. Which one? Regular R squared, exactly, okay? How about the rest of the class? Do you understand this? So that's two questions. In order to measure the goodness of speed, model selection between this larger model and small model, which can be used as an indicator. The model is better. That's the adjusted one, because it's not influenced by the dimension of your problem. And when it comes to explain the portion of the total value in Y that can be accounted for by the variation X, all the X here, that will be the regular Y, because that's between R squared and the relation between R squared and S. What is R? That is the Y hat minus Y bar, summation of them squared. Summation of Y hat minus Y bar squared. Okay, so in the Y hat, you basically have all the estimated data, right? Zero, Y hat. So you also include all the X. So basically, the variation in Y operates adjusted by its mean, which is estimated with zero. After that, the mean is the linear combination of the X. Okay, so in that case, the variation in Y is explained by all you can multiply by the X. So you can with J. That's a complete definition. Completely include SSR because you use Y hat and SSR. But after you adjust here, you no longer have that adjustment. So to account for the variation Y that can be explained by X, you use the old definition bars. I hope it will be the part is not that well. Sometimes people get confused. Is that all here? No. All right. So don't get confused for another R. So far we have find the common R's. We have your regular R squared. We have R squared adjusted. We also have R squared RCO. Okay. Remember what is used of what? So for this R squared, regular R squared, we define it as R over SIC. We also divide R linear correlation between Y and X. So you can plus or minus square root of R squared. This is correlation between what? Y and X. Linear correlation. When we say correlation, coefficient is always linear correlation. Sometimes we forget the word linear